For the first time ever, we saw the shape of a supernova explosion in real time. The blast was so immensely powerful that it was literally ripping the surface of the star right in front of our eyes. Now we can finally understand what actually happens inside a star right before it blows apart. You see, massive stars fight against their own gravity their whole lives. They burn hotter and hotter elements to keep themselves from collapsing inward. But eventually, the star starts producing iron in its core. And this is a problem. Unlike many other elements, iron doesn't create energy inside the star. So once this process starts, the star loses its support system and gravity wins. The core collapses inward insanely fast, and then everything around it crashes down toward the center of the star. Once all that falling material slams into the dense core, it rebounds and creates a gigantic shockwave, and that's what rips the star apart. Scientists didn't fully understand how that part worked, but new observations helped them. They could watch the shockwave while it was actually moving through the outer layers of the star. Even better, they could see the shape of the explosion, and it wasn't what anyone expected. The blast wasn't perfectly round. It was slightly stretched in one direction. It may sound unimportant, but it can actually change how we understand supernovas and their final moments, when a star suddenly releases more energy than our sun will produce during its entire lifetime. The exploding star was first spotted on April 10, 2024, by a system called ATLAS, which scans the sky for dangerous or unusual objects. Just a few hours later, scientists already pointed one of the world's most powerful telescopes, the Very Large Telescope in Chile, directly at the discovery. For a very short time, the star's real shape and the shape of the explosion were both visible. But soon after, clouds of superheated gas hid everything. The star was a red supergiant. That's an enormous star close to the end of its life, about 12 to 15 times heavier than our sun. Normally, when we think of a supernova, we imagine a giant flash of light illuminating space. That flash happens when the shockwave from the collapse gets through the star's outer layers and releases a truly enormous amount of energy. For many months, the explosion shines brighter than whole galaxies, but the first few hours are the most important, and usually impossible to study because they pass super quickly. This time, scientists used a special technique that studies how light waves move and scatter. It helped them notice that the exploding material looked almost olive-shaped. Later, the explosion slammed into the gas surrounding the star and its shape flattened. But it still kept the same overall direction even while it was expanding outward into space. That detail may actually help us solve one of the biggest mysteries about supernovas. Right now, scientists have two main ideas about what can actually cause a giant dying star to explode. The first idea claims that tiny particles called neutrinos blast out from the collapsing star and heat everything around them, but the heating happens unevenly. So, the explosion becomes messy and unstable. That's why the star blows apart in a rough, uneven way. There's another theory. It sounds much more extreme. Some scientists think that the star sends out enormous streams of energy from deep inside its core right before exploding. These streams work like giant cosmic drills. They punch through the star and force the explosion outward in a more organized direction. The new supernova can tell us which idea is closer to the truth. The telescope data showed that the explosion had a very clear shape and direction, almost from the very beginning. It didn't look random or chaotic. The blast stayed surprisingly symmetrical while it expanded through space. And that's a big clue. The explosion looked more like something fueled by powerful streams of energy rather than a messy neutrino blast. This discovery changes a lot. For decades, researchers have been arguing over what really happens inside a massive star during its final seconds. And now we can finally figure out the mechanism behind those gigantic explosions. And if you think that all supernovas happen insanely far away from Earth and don't affect us in the least, let me tell you this. Right now, Earth is drifting through the leftovers of a giant explosion that happened somewhere in space a very long time ago. And scientists just found some proof inside ancient Antarctic ice. Researchers were studying ice that had formed up to 80,000 years ago and discovered tiny traces of something called iron-60. You see, most iron on Earth is a normal version called iron 56, but iron 60 is different. It's radioactive, extremely rare, and it slowly disappears over millions of years. And it usually forms during supernovas. In simple terms, scientists found microscopic pieces of star ash frozen inside the ice. At first, researchers were confused. The Antarctic snow where they discovered this kind of iron was less than 20 years old. It made no sense. If a nearby star had exploded recently enough to spray this material onto Earth, we would have definitely noticed this. The sky would have lit up with one of the biggest cosmic explosions in history. But there was no supernova. This meant something else was going on. Eventually, they figured out the truth. Apparently, our entire solar system is currently moving through a gigantic cloud of gas and dust. Scientists call it the local interstellar cloud. For years, researchers suspected that this cloud may have formed after one or more huge stars exploded nearby a long time ago. And now, the discovery of iron 60 proves this idea. The material likely came from an ancient supernova that once sent its radioactive debris across space. Even after all this time, tiny particles from that explosion are still floating through our region of the galaxy, and some of them are literally falling onto Earth. To test the idea, scientists dug into old deep-sea sediments and ancient Antarctic ice cores going back 30,000, 40,000, and even 80,000 years. And every deeper layer gave them more evidence. The levels of iron 60 changed over time exactly the way they would have if Earth had been slowly drifting through a giant cloud filled with ancient supernova debris. And its microscopic radioactive particles have been falling on our planet for thousands of years. By the way, iron 60 was extremely difficult to find. Scientists started with around 660 pounds of Antarctic ice. After processing it, they started searching through trillions of atoms to spot just a few tiny traces of iron 60. But the search paid off. Researchers are sure that this ancient stellar debris may help us better understand the strange clouds surrounding our solar system. We can also learn more about the powerful cosmic events that had been affecting our galaxy before we even existed. Now, it might come as a surprise, but many of the elements you're made of come from supernovae. It can be anything, from the oxygen you breathe to the calcium in your bones. The iron in your blood or the silicon in your computer might have first appeared in the core of a star. And when a supernova exploded, it unleashed a storm of nuclear reactions, which in turn produced lots of building blocks making up the world around us. Supernovae are like giant particle machines in space. When a star explodes, the blast wave crashes into the gas around it and creates a super powerful magnetic storm. Tiny particles get trapped inside, bounce around, and speed up to insane speeds. Eventually, some of those particles shoot across space as cosmic rays. And then, some of them hit Earth. They slam into our atmosphere, smash into our atoms, and create invisible showers of particles that rain down on us all the time.
Imagine you're looking up at the sky on a clear night, and you see all those beautiful stars twinkling up there. Well, one of them is Betelgeuse, a celebrity among stars. If you want to catch a glimpse of it, look up at the Orion constellation. It low-key looks like an archer holding a bow, and you can spot Betelgeuse as the reddish-orange dot on their shoulder. It's one of the brightest stars in the sky, so it's hard to miss. Betelgeuse is not your ordinary star. First of all, it's gigantic, up to 1,000 times the size of our sun. Can you imagine that? It's so enormous that if we could somehow replace our sun with Betelgeuse, it would engulf all the inner planets, including Earth. And here's another fun fact. When we look at Betelgeuse, we're actually looking back in time.
Yep, you heard it right.
Betelgeuse is about 600 light years away from us, so the light we see today actually left the star 600 years ago.
It has quite a history. This star has been shining brightly for millions of years. Long ago, even before smartphones and telescopes, ancient Sumerians were the first to spot Betelgeuse in the sky. and it's been a diva this entire time. For example, in 1866, Betelgeuse became one of the brightest stars in the night sky. It was so dazzling that people could see it even during the day. Astronomers all around the world went bananas documenting this extraordinary event. Since then, Betelgeuse has been playing hide and seek with us. It all started when Betelgeuse started to dim back in 2019. Since then, it likes to dim and brighten sporadically. But these changes in brightness tell us about something important. As we mentioned, Betelgeuse was always a bit of a troublemaker. It's been living a fast and furious life. Because of that, it has been burning its fuel at an incredibly fast rate. The changes in the star's brightness are clues that Betelgeuse is approaching the end of its life cycle. The drama intensified when the Hubble Space Telescope snapped jaw-dropping images of Betelgeuse, like it was getting ready to blow its top. All this made scientists think that the star is close to retiring in a dramatic way. It's about to go supernova. So picture a star partying hard, powered by the fusion of hydrogen atoms. It's like the star's own energy drink, but just like any party, the fuel starts to run out. That's when things get interesting. As the star guzzles up its hydrogen fuel, it slowly begins to run on empty. It can't sustain itself anymore. So now, it's time for the grand finale. This finale is called supernova. The star collapses in on itself like a deflating balloon. The pressure and temperature inside skyrocket to mind-boggling levels, and this celestial tantrum triggers a colossal bang. So you can see why observing Betelgeuse is like having a front-row seat to the spectacular drama. But here's the big question. When will this happen? Well, the answer is not as simple as setting a timer. You see, stars have their own schedules, and Betelgeuse is no different. It could be tomorrow, or it could be thousands of years from now. Scientists have come up with only a rough estimate. They believe that Betelgeuse will go supernova within the next 100,000 years. Quite a spread, huh? Sure, that sounds like forever to us, tiny humans. But in the vastness of the universe, it's just a blink of an eye. But there's a chance, just a tiny chance, that Betelgeuse could surprise us all and go supernova much sooner. Considering its dips in brightness, we might be in for a show within the next few hundred years. We'll just have to wait and see. Now, if Betelgeuse does go kaboom, what will happen? Well, get ready for a show like no other, folks. When a star collapses under its own weight, it unleashes a cosmic firework of epic proportions. The star releases a crazy amount of energy in the form of light and heat. Betelgeuse's supernova is going to be extra special. It's like the superstar of supernovas. It will shine so brightly that it might even outshine the other stars in the sky. Picture that, Betelgeuse stealing the spotlight. The show could be so bright that you won't need a telescope to catch a glimpse. Nope, you'll be able to see it with a naked eye. It might even be visible during the day, making the sky look like it's hosting the coolest rave ever. After that, the supernova will keep us entertained for weeks. It will be like having a second moon in the sky, shining as bright as the full thing. Imagine that, 2 moons dancing together in the night. After several weeks of lighting up the night sky, Betelgeuse's supernova will slowly fade away, but it would leave behind a souvenir, an ethereal remnant. It's like a fading memory of the star's epic performance. This remnant, too, would slowly fade away over the course of several months. But it's not just about the light show. The boom will send out powerful shockwaves, and we might actually feel them right here on Earth. It's like the universe giving us a gentle tap on the shoulder, saying, hey, look at this amazing spectacle. How dangerous will it be for us? Well, we know that Betelgeuse's supernova would send dust and gas shooting into the atmosphere. It's like a big space sneeze. And this sneeze could cause a decrease in global temperatures. We're talking serious climate impact here. It could even lead to a mini ice age. But these are just assumptions. We don't know for sure if the consequences will really be that serious. But, of course, we want to be prepared for this event just in case. That's why scientists are studying Betelgeuse closely. But, in addition to serious scientific research, Astronomers also have a blast of celestial comedy. Jokes are flying left and right. Someone has even created a Betelgeuse status account, which you can check yourself. So, as you can see, the star is keeping us on our toes. Astronomers keep observing it, and they need our help too. They want us to keep an eye on Betelgeuse and report any changes we see. How do you do that? First off, channel your inner astronomer and observe Betelgeuse. Take a peek at the star and note down what you see. Is it twinkling, shining, or feeling a bit dim? Jot it all down. Then be a superstar yourself and report your observations to the astronomers. Your observations will help them track Betelgeuse's journey towards its big supernova moment. You can also join in on some citizen science projects. They're super fun and easy, trust me. One cool project you can jump into is the Betelgeuse Brightness Monitor. By participating, you help scientists keep tabs on how bright Betelgeuse is shining. Your contribution can make a real difference. So join the monitoring team. You'll be part of something amazing, and who knows? Your observations might even help predict when Betelgeuse will show off its supernova magic. By doing that, we can assist them in monitoring this superstar and learn more about the fascinating world of stars. But that's how we can help scientists to predict this event. Now, how can you personally prepare for it? First things first, you'll need the right gear to catch all the supernova action. A trusty telescope is like your front row ticket to the starry show. It'll bring you up close and personal with Betelgeuse's performance. And remember, you'll need special eyewear to shield your eyes from the intense burst of light. Safety first. And of course, prepare in case it decides to mess with our climate. Stock up on essentials, like warm clothes and supplies, just in case we experience a mini ice age. But let's just hope it won't happen. So keep your eyes on the night sky, my friends. Betelgeuse may not be ready to blow up just yet, but when it does, it will be a sight to behold. Until then, let's enjoy the twinkling stars. And remember, there's always something extraordinary happening in the vastness of space.
All the stars we see, including our sun, are in a balance of powers. Stars are very heavy objects, so they have strong gravity, which presses them from the outside and makes them shrink. But inside a star, while it burns fuel, there are nuclear reactions that produce incredible amounts of energy. This energy is the light and heat that we feel during the day. But most importantly, these reactions increase the pressure inside the star and create a force that is fighting with gravity. So as long as the star has a full tank, it's safe. But then, the fuel runs out, the pressure inside the star falls, and the gravity wins. A star the size of our sun can shine for about 10 billion years. Specifically, our lovely sun is about 4.5 billion years old and has already burned half its fuel. The next stage in a star's life comes when it runs out of juice. Internal pressure drops, but gravity continues to press. At some point, a star simply collapses under its own weight and shrinks to the size of its core at the speed of almost a quarter of the speed of light. In less than half a second, a huge star turns into a small and dense object. This rapid collapse creates incredible shock waves that cause the upper layers of the star to explode. Now, an incredible amount of energy and matter is thrown into outer space. At this moment, luminosity of the star increases millions or even billions of times. This is the flash that our scientists can see with super powerful telescopes. But the light from this explosion doesn't reach our planet until many years later. So in fact, this star has long since faded. There are several options at this point. It all depends on the size of the star. If its mass is small, about the mass of our sun, then for several months, this flash will become brighter and brighter until it reaches its peak. Then, the energy of the explosion will begin to dissipate, gradually fading and cooling down. A few years will pass, and the temperature of the former star will will match that of space, and it will simply cease to exist. But the heavier the star, the more interesting the events will be. Heavy stars burn their fuel too quickly and have a much shorter lifespan. Stars weighing about 8 masses of the Sun can collapse into a rather unusual object, which is rarely found in the universe, a neutron star. This dull ball is only 6 to 12 miles wide and covered with a hard metal crust about half a mile thick. Neutron stars can weigh about 2 suns and have a strong gravity force. If you feel comfortable and in good shape on Earth, you wouldn't even be able to lift a needle or a match here. What's more, you would be pressed to the surface like a pancake and just unable to move. But there are stars dozens of times heavier than the Sun. An explosion of such a supernova, which weighs at least 40 times more than the Sun, gives birth to the most inexplicable and mysterious object in the universe, a black hole. At first, an incredibly bright explosion occurs. A shockwave spreads, carrying dust and matter of the former star around like a fog. And at the place of the explosion, only a small black disk is left. This black abyss is the heaviest object in the universe. It's so heavy that its gravity curves space-time around it. Yes, the closer you are to a black hole, the slower time will go for you. If you could get close enough to one of them, spend a couple of minutes in its orbit, and return to Earth, you would simply not recognize your home. 1 minute near a black hole can be a month, a year, or a decade on Earth. This depends on how heavy the black hole is. But don't get too close. The force of its gravity is so strong that even light can't escape from it. Humanity also knows about the existence of supermassive black holes. They gradually build up their mass, feeding on different cosmic objects just like a predator. Usually, such supermassive black holes lie in the centers of galaxies, and their gravity is so strong they can hold countless stars near them. For example, this is the only photo of a black hole, which is located in the center of the Messier 87 galaxy. The orange glow around it is its event horizon. That's the remains of the light from the objects this black hole has swallowed. You're quite safe though. The closest black hole is 1,120 light-years away. But supernovae can explode not only when gravity wins the fight with the star's internal forces. Sometimes the opposite happens. The nuclear fusion inside the star begins to affect much more matter than normal. The pressure inside a star increases, and it defeats the force of gravity that exerts pressure on the star from outside. At this point, there's a boom! This never happens by itself, and this type of supernova is only possible in binary star systems. 2 stars are spinning around each other. One star begins to swallow the substance from the other. Then, the nuclear reactions inside it are no longer in balance, and a supernova explodes. For some time, scientists believed that such an explosion could occur in 2022. There's such a binary system in the Swan constellation at a distance of 1,800 light-years from the Sun. The luminous red nova should have occurred here. Such a red flash would have been visible to the naked eye for months. And after the explosion itself and the merger of 2 stars, a new, hotter, and heavier star was to appear in their place. But a new analysis of the data revealed a calculation error, and this event will not happen soon after all. So now we see that a supernova explosion is a very dangerous event, and it can cause great harm to our planet if it happens close enough. The main danger is gamma rays. This is the radiation that comes from the explosion. When these rays reach the Earth, they affect our space shield, the atmosphere. They reduce the ozone layer and make us vulnerable to solar radiation and cosmic rays. In this case, all life on the planet is in incredible danger. And the bad news is that such an explosion could happen quite soon. Betelgeuse, the brightest star in the night sky, about 17 times larger than the Sun and 8.5 billion years old. It's begun to exhaust its fuel reserves. Scientists predict that this giant will explode like a supernova at any moment within the next 10,000 years. So it may happen in a few centuries or even tomorrow. Everything will happen as follows. Betelgeuse will collapse in a fraction of a second, and then it will explode so brightly that it will look like a second moon in the night sky. We will observe a new bright spot in the sky for weeks or even months. But then, it will begin to fade until it completely disappears. Not without a trace, though. In its place, there will be a neutron star, weighing 1.5 times the Sun. It will be one of the biggest events that humanity has ever seen. Still, we have nothing to be afraid of. Betelgeuse is about 550 light-years away from us, so its X-rays and ultraviolet light will not affect us. A much greater danger is posed by the release of material that occurs in a supernova explosion. But this shouldn't make you worried either. The shockwave won't reach the Earth until 6 million years later, and it will be suppressed by the oncoming solar wind. So if we see Betelgeuse explode today, it will be an epic sight. But, in fact, the star will not exist at the time, because it will mean the event itself happened almost 6 centuries ago. It's just that now the light from it has reached us. Some scientists believe that the Ordovician Silurian extinction events, which occurred almost 500 million years ago, happened exactly because of a star explosion. Then, almost 60% of marine vertebrates went extinct. Yet, it was not a supernova, but a hypernova. That is what scientists call explosions of stars 100 to 150 times larger than the Sun. In addition to the abnormal weight, the star must rotate very quickly. Such objects are very rare. In our galaxy, there are few of them, and scientists believe that hypernovae occur about once in 200 million years.
One of the biggest stars we've ever found is wobbling on the edge of disaster. And it won't go quietly. It might collapse in on itself and instantly become a black hole, or explode in a blinding supernova. It might even crash into its companion star, and we could probably see it. The star in question, WOH G64, wow, that's a mouthful, I'll nickname it Jerry. So Jerry is a red supergiant. These are huge stars at the end of their lives. Like cosmic seniors, they've already burned through most of their fuel, puffed up to an enormous size, and are getting ready to explode as a supernova. They're cooler on the outside than many other big stars, that's why they glow red instead of blue or white. Still, the biggest and brightest of these stars are kind of a mystery. Astronomers aren't totally sure what happens to the most extreme ones right before they explode. When they look at the sky, they don't see as many ultra-bright red supergiants blowing up as they would like to. Instead, they see hints that some of them might change color and heat up again before the end. One famous example is our star called WOH G64 in the Large Magellanic Cloud. That region is basically a stellar nursery. It means it's packed with thick clouds of gas and dust where stars are born. It's the perfect place to grow something extreme. Now, for decades, we considered Jerry one of the most outstanding red supergiants ever found. It's enormous, it's incredibly bright, like me, and losing mass like crazy. It's also surrounded by so much dust that it looks heavily wrapped up, like it's hiding inside a thick cosmic blanket. But recently, something weird happened. The star's light signature started to look completely different, as if this red supergiant had changed identity. Now scientists think Jerry isn't just a single star. It's probably a rare pair of stars locked together in a relationship called a symbiotic binary system. In this system, the red supergiant seems to have transformed into something hotter and more unstable, called a yellow hypergiant. Now, yellow hypergiants are like the middle phase before total destruction. They're enormous. Some are so big you could fit billions of suns inside them. But they don't last long. This stage is brief and chaotic, like a star pacing nervously before its final act. Yellow hypergiants are extremely rare because they represent a short transition between the red supergiant phase and the final explosion. We know of only a few dozen confirmed examples. Now, why would that transition happen? One possibility is stellar drama. Ooh, what could happen? Well, as we know, Jerry isn't alone. It likely has a companion star. The two may have interacted so intensely that the red supergiant blew off a huge chunk of its outer layers. Imagine two stars spinning around each other so tightly that one basically starts stealing material from the other. That lost material could have formed a massive cloud, a shared envelope that briefly swallowed both stars. But there's another possibility. Even without interference from a companion, a star this massive can become unstable on its own. It might have gone through a huge eruption that lasted more than 30 years and is now settling down into a hotter yellow phase. Whatever it is, this is incredibly rare, like watching a star evolve in real time instead of over millions of years. In any case, after watching this monster star suddenly change before their eyes, astronomers now think it may be getting close to the end. A new study claims the star could be on the verge of exploding in a massive supernova. Or, since it's so unbelievably heavy, it might skip this step completely and collapse straight into a black hole. Now, Jerry was discovered about 50 years ago and labeled a red supergiant. It has about 30 times the mass of our Sun. But the really mind-blowing part is its size. If you drop this star into the middle of our solar system, it would stretch all the way past Jupiter. Stars like this live fast but not long. Jerry is only about 5 million years old. That might sound ancient until you remember our Sun is 4.6 billion years old and still going. The problem is, massive stars burn through their fuel super fast. That's why they shine so bright, grow to ridiculous sizes, and then go out in a blaze of glory. Now, we don't know how it'll happen, but because of its enormous mass, Jerry's demise won't be quiet. In cosmic terms, it could happen soon, meaning within a few hundred to a few thousand years. It might explode in a supernova, blasting its outer layers into space. Or it could collapse inward so violently that it forms a black hole on the spot. There's even a chance it could eventually slam into its companion star. So let's say our red supergiant tears itself apart in a supernova. Then we need to learn more about these space fire shows. Supernovas are gigantic explosions that happen when massive stars finally collapse. They're incredibly important to how we understand the universe. Astronomers use certain types of supernovas, like measuring sticks, to figure out how far away galaxies are. In fact, it was supernovas that tipped scientists off in 1998 that the universe wasn't just expanding, it was actually speeding up. But there's one problem. Even though supernovas are powerful and bright, they happen incredibly fast. Catching the exact moment a star explodes is like trying to photograph a lightning bolt at the exact second it strikes. But an international team of astronomers says they managed to do exactly that. They got the earliest and most detailed look ever at a supernova right as it was blowing apart. Using the European Southern Observatory's Very Large Telescope, they basically watched the shockwave from the collapsing star blast through its surface. For the first time ever, they could actually see what shape the explosion had. And that shape does matter. When a massive star runs out of fuel, things go bad fast. For millions of years, the star balances two forces: the nuclear fusion in its core pushing outward, and gravity pulling inward. But once the fuel is gone, gravity wins instantly. The outer layers crash inward, slam into the collapsed core, and rebound outward in an intense shockwave. That shockwave tears through the star and blows it to pieces. The result is a supernova. That's the basic idea. The details of how that shockwave forms have been hard to pin down, because supernovas are nearly impossible to catch in the act. Out of the trillions of stars out there, astronomers would need to be already looking at the exact right star at the exact right moment, and it would have to be close enough to study before expanding gas clouds block the view. This time, they got lucky. The explosion happened about 22 million light-years away, which also means it happened 22 million years ago. Think about that. Astronomers spotted it quickly and managed to start observing it within just 26 hours after it was first detected. In supernova terms, that's incredibly fast. They used a technique called spectropolarimetry, basically a way of studying how light is scattered and how its vibrations are aligned to figure out the shape of the blast. What they found was surprising. The explosion wasn't perfectly round. Instead of expanding like a smooth sphere, the shockwave stretched out slightly, more like an olive than a ball. When the blast slammed into the gas surrounding the star, it flattened, but it still expanded evenly along that stretched shape. It means the very first light and material didn't shoot out evenly in all directions. The explosion had structure right from the start, and that structure gives clues about what was happening deep inside the star when it collapsed. Now, here's another interesting fact. The star that went supernova was a red supergiant, about 12 to 15 times the mass of our Sun. And based on how many red supergiants are out there, astronomers expected to see lots of them exploding. But for years, they didn't see many. It was almost like these giant stars were disappearing quietly. More recent observations from the James Webb Space Telescope suggest they probably are exploding. We just couldn't see them clearly before. Maybe because dust and gas were hiding the blasts. And now, this new observation suggests their explosion might actually follow a common pattern, with a clear stretched shape rather than a perfect sphere. In other words, these cosmic explosions may be more organized than we thought. The Earth. Frozen and alone, exiled into deep space. Jupiter, the only remaining planet orbiting the Sun. No, it's not a premise for a disaster movie. It's one of many real scenarios scientists explored in their latest simulations. This time, the threat isn't the Sun swelling or a giant asteroid knocking planets into it like a cosmic bowling ball. It's something quieter and possibly already on its way. A recent study examined the potential consequences of a passing star coming too close. One such flyby could send planets crashing, flinging them into space, or mess with their orbits just enough to cause climate changes. But what are passing stars, and how likely is that to occur? Passing stars are normal stars, like our Sun, that move around the Milky Way. Since everything in space is always moving, sometimes stars pass near each other. Usually it's not a big deal. But if a star gets really close, its gravity can tug on planets like Neptune. That tiny tug can slowly change how the planets move, like a ripple spreading through the whole system. Scientists study these close encounters because, even though they don't happen often, they can have big effects over millions of years. They help us understand shifts in planetary orbits and how they may have shaped Earth's past. In fact, one theory suggests that a flyby 56 million years ago is what caused great climate change when Earth's temperature rose by up to 14 degrees Fahrenheit in just a few 100,000 years. That huge temperature jump changed life on Earth, leading to the evolution of some species while causing others to disappear. Even though it's impossible to prove whether there was a flyby a long time ago, we do know that events like this could mess with Earth's orbit in the long run. That's in the past, but what about the future? So far, we know that the solar system will have a close encounter with another star called Gliese 710 in about 1.3 million years. Gliese is moving towards us and is projected to pass within 10,000 astronomical units of the Sun. It won't come close enough to throw planets off, but it could still send icy comets from the Oort cloud our way, like a bored kid tossing a snowball without looking. One might hit something, but probably won't. However, in a recent study, scientists wanted to explore a more extreme scenario. What if a star passed even closer, say just 100 astronomical units from the Sun? That's about 100 times the distance from Earth to the Sun. From our point of view, it's almost unimaginably far, but in space, it's practically brushing shoulders. They ran thousands of long-term simulations covering up to 5 billion years of our solar system's future, and it turns out it doesn't take much. Just one close encounter can be enough to disturb the outer planets, like Neptune, and set off a slow-motion chain reaction that ripples inward. Over time, that gentle nudge can throw the whole system into chaos, a true cosmic butterfly effect. The good news is that even in this worst-case scenario, in 95% of simulations, the passage is nothing to worry about, and all the planets remain in place. However, in the remaining 5%, well, it's one disaster after another. The most frequent casualty in these simulations was Mercury. In nearly half of all unstable scenarios, Mercury ends up on a doomed path straight into the Sun. It's the smallest planet and the closest to our star, so it's especially susceptible to gravitational nudges, whether from the gas giants or from a disturbance rippling inward from a stellar flyby. When Mercury spirals into the Sun, you might think it's game over for the rest of the planets, but that's not always the case. Sometimes the system absorbs the loss and restabilizes, like an orchestra that keeps playing even after one violinist falls off the stage. Oops. Funny enough, Mercury already has a chaotic orbit, the most stretched and tilted of all major planets, and some studies already consider its fall into the Sun in the distant future inevitable. Now, Venus has a slightly better chance in these chaotic scenarios. It doesn't get ejected or swallowed by the Sun as often as Mercury, but it's far from being safe. Most of the time, the instability happens after Mercury goes rogue and disrupts Venus's orbit, nudging it into a slow-motion crash course with Earth or Mars. Even without the interference from field stars, long-term simulations show a tiny but real chance that Venus could eventually collide with Earth just from the way Jupiter affects Mercury. A Venus-Earth collision would result in both planets being completely destroyed. Oh well. A similar fate awaits Mars. According to simulations, in about 0.3% of cases, it either gets flung out of the solar system or collides with another planet. Mars is smaller and lighter than Earth, with weaker gravity, which makes it easier to knock it off track. What's interesting is that even in some cases where Mars is lost, Earth often manages to stay in place. Jupiter happens to be the heavyweight champion of the solar system, the proud owner of its own cloudy belts. Thanks to its massive size and strong gravity, it acts like an anchor, keeping everything else in check. There are 392 scenarios out of 12,000 simulations where all but one planet vanished, with Jupiter being the last one standing. Its stabilizing influence helps prevent smaller planets from going off course, and in some cases, it even helps the system recover after a disruption. Saturn, while less massive, seems to be Jupiter's loyal partner. But models show that when Saturn shifts its orbit abruptly, it can send gravitational ripples, known as secular resonances, straight into the inner solar system, nudging the orbits of planets like Earth and Mars. Finally, the most vulnerable ones are Uranus and Neptune. Sitting at the edge of the solar system, they're the easiest to knock loose, and in many simulations, they get ejected entirely. That loss sends gravitational ripples inward, disturbing the rest of the planets over millions of years. Even a tiny shift by 0.1% in Neptune's orbital distance can throw the whole solar system out of sync. The balance of gravitational forces would shift, forcing Jupiter and Saturn to readjust, which would push the disturbance toward the inner planets, destabilizing everything. Which brings us to the big question: what about Earth? While most simulated models leave Earth untouched, about 0.2% of the simulations end with Earth either colliding with another planet, Venus, or being thrown into the Sun. Out of 12,000 simulations, in 23 of those, Earth ends up as the only one still orbiting. But that's only if we don't include the Moon in calculations. With the moon included, Earth becomes harder to predict. Our satellite could crash into Earth, get ripped away by a passing star, or destabilize our orbit over millions of years. Once again, this is a worst-case scenario, and while the odds are really, really small, it's not impossible. So, with that in mind, let's entertain the idea and see what would happen to Earth if it were to end up exiled from the solar system. Earth would become what scientists call a rogue planet, drifting through interstellar space with no sun to anchor it. The surface would quickly freeze, with temperatures dropping to hundreds of degrees below zero. But surprisingly, life wouldn't vanish completely. Earth's core would stay hot for billions of years, powered by radioactive decay and leftover heat from its formation. That heat could keep underground pockets warm. Scientists believe that this is the case with icy moons like Europa or Enceladus. Life might cling on in different caves or buried oceans. It wouldn't be a thriving world, but it wouldn't be completely empty either, at least for a while. Just cold, quiet, and alone. A ghost of a once lively world. And somewhere out there, maybe another civilization will look up, spot a faint blue dot drifting by, and curiously start running simulations of what might happen if this blue planet were to get really close, say just 100 AU from their sun. Now, let's think for a moment. What if, instead of building spaceships to move across the stars, a super advanced civilization decided to turn their entire star system into a spaceship? That means a whole sun, the planets, all the asteroids, zooming through the galaxy together. That's what one philosopher, Clement Vidal, suggested in his recent space theory. There could be countless reasons why these extraterrestrials might decide to explore space. Maybe the star nearby is about to go supernova, blowing up and destroying everything nearby, including their home system. Or maybe they're searching for new resources somewhere in outer space or trying to spread life. But our galaxy has a minor problem. It's incredibly huge. So even if they move with the speed of light, getting from one star to another would take a gazillion years. However, if we could just move our entire solar system, that would be convenient. We wouldn't have to change a thing or look for another star system and planet. How, though? Well, they'd use their own star as an engine. Literally, a stellar engine. All they'd need to do is push their star and everything orbiting it in a specific direction. You must cause the star to spit out material unevenly, creating a kind of thrust. It's like our rocket propulsion, but applied to entire stars. When more material ejects on one side of the star than the other, it acts like a rocket, slowly nudging the entire system along. Over time, they could steer it to wherever they want. Now, this isn't just some goofy idea. Well, maybe. But many scientists have proposed different models for how a stellar engine could work, and how we humans could use it. The most famous one is called the Shikhatov thruster. Here, the idea is to use a giant reflective mirror to push a star gently in one direction by reflecting its sunlight. Other designs propose ejecting mass from the star itself. Of course, that'd be insanely hard for humans to pull off, but a super advanced civilization might just do it. And it might not be as hard as it sounds. There are already stars in the galaxy that move at incredible speeds. They're called hypervelocity stars. These stars are so fast they can escape the galaxy itself. Their story begins in the heart of the Milky Way. At the center of our galaxy lies a monster, a supermassive black hole with gravity so intense nothing can return from it. We even took a shot of it a while ago. Remember this one? It's called Sagittarius A star. We start with a pair of binary stars. They are similar in mass and orbit each other. Sometimes they stray too close to a black hole. When this happens, one star can get captured by the black hole, its fate sealed, while the other gets the wildest roller coaster ride of its life. It's like a crazy slingshot. It's hurled outward with unimaginable force. These exiled stars gain incredible speeds, like over 1 million miles per hour, and become hypervelocity stars. Now, this doesn't happen that often. Maybe one hypervelocity star is flung from the galactic center every 100,000 years. And with over 100 billion stars in our Milky Way, finding them is worse than needles in a haystack. But even so, we managed to find about 1,000 such exiles in our galaxy. But anyway, could these superfast travelers be extraterrestrial starships? Maybe it's some wild move other civilizations decided to pull off, getting slingshot by a black hole so they could travel wherever they want at wild speeds. Now, most hypervelocity stars studied so far are single stars. But what about binary systems themselves? This binary system we mentioned would make this whole process of turning a star into a spaceship much easier. Another civilization could focus their efforts on one star in the pair. The interaction between the two stars could be used to fine-tune direction and spin, like a built-in steering wheel. It would also help use energy more efficiently. Let's try implementing this. Take a neutron star. This is what's left behind after a huge star reaches its end. Its tiny, incredibly dense version. These little neutron stars are often paired with the small and normal ones. Neutron stars have some insane gravity. This could help them provide the energy needed to push the whole system. So, if an extraterrestrial civilization decided to build a machine like this, they'd probably do that near a binary system like this. But would our extraterrestrial friends settle for basic binary systems? Actually, they could go even further, for a wilder, more efficient option – Black Widow pulsars. Ooh. This is the most dramatic type of a binary system. A neutron star spins with unbelievable speed and doesn't just hang out with its companion star, but slowly devours it. These two create such a thrilling gravitational dance, it's both destructive and beautiful. As the neutron star spins, it just keeps flinging torrents of high-energy particles right into space, and all of them clash with the fragile remnants of its poor little partner. Can you imagine that this energy could be harvested? All these options – hypervelocity stars, binary systems, and spider pulsars – would be great for this stellar engine project. A civilization that had this type of engine could gradually explore and colonize the galaxy, all while having its own energy source and planets with them. But how do we know whether these starships actually exist? Astronomers look for something called technosignatures. These are little clues and hints, something that looks unusual for normal celestial bodies. For example, things like weird motion in binary systems, or stars that eject material in weird, unnatural ways. They could all mean that there's some technology being used there. We haven't any evidence of that so far, but there are candidates. There are two Black Widow pulsars that look strange. Clement Vidal, the author of the paper, says that we should look at those systems closely, just in case. And even if it turns out that this idea is incorrect, we can still use it as an inspiration for ourselves. If extraterrestrial civilizations won't do this before us, we might just pioneer that technology. And speaking of technosignatures, besides these starships, NASA is also looking for signs of megastructures in space. Maybe other civilizations don't treat their stars as some sort of chariot horses, but simply use them as a giant energy source. Life needs energy to survive, whether it's microbes, animals, or smart human-like civilizations. As life evolves, its energy demands skyrocket. Now, we started with fire, then moved to coal and oil, and now we're exploring solar power. One day, we might start harvesting the power of our sun directly. Maybe advanced extraterrestrial creatures are already doing this. On Earth, a physicist, Freeman Dyson, proposed the idea of a Dyson sphere, a huge structure around a star that can harvest its energy, like one enormous solar panel, but right around the sun. Sounds crazy to us, but we might find it somewhere out there. Once again, astronomers are checking technosignatures to spot those. For example, they've analyzed data from over 5 million stars trying to find weird signals, flickering, or anything that can't be explained by dust or similar stuff. If we're talking about a Dyson sphere, Then, eating a star's energy would make it radiate a lot of infrared heat. That means we'd notice a telltale glow. Eventually, they narrowed it down to 368 possible suspects. They checked those, and only 7 stars remained. These stars show strange light patterns that we really can't explain yet. These stars are mostly small, faint red dwarfs. One of them is especially famous, called Tabby Star. It blinks and dims in weird random ways, dropping in light by 22% from time to time. Astronomers aren't sure whether it's some broken moon flying around it, dust, or a Dyson sphere. In any case, they'll keep looking for these techno-clues. Let's hope we'll learn the truth someday. Now see here, astronomers have recently discovered a neutron star, also known as a dead star, spinning at an extraordinary speed of 716 times per second. It makes it one of the fastest spinning stars we've ever found in the universe. And it's not just about its speed. The surface of this neutron star is erupting with super powerful explosions almost non-stop. But before we dig deeper into the mystery of this neutron star, let's figure out what these stars really are. They form from the remnants of massive stars that are at least 8 times the mass of the Sun. When such stars exhaust their nuclear fuel, they can no longer counteract the force of gravity pulling their matter inward. This leads to the collapse of their cores, triggering a massive supernova explosion that blows away the outer layers of the star. What's left behind is an ultra-dense core. That's a neutron star. These stellar remnants are incredibly small, typically just 12 miles wide. At the same time, they pack in more mass than the Sun. The density of neutron stars is also overwhelming. Imagine taking the mass of 2 suns and squeezing it into a sphere about the size of a city. A single teaspoon of neutron star material would weigh around 10 million tons. That's the same as the combined weight of 85,000 blue whales. Such an extraordinary density is what gives neutron stars their immensely powerful gravitational fields. When matter falls onto a neutron star, it accelerates to speeds of millions of miles per hour before slamming into the surface. The energy release from such impacts is truly astonishing. Now, despite its name, inside a neutron star, there are not only neutrons. A few protons survive down there too. Now, normally, protons repel each other since they have the same positive charge. But in a neutron star, that crushing gravity forces them so close together that the strong nuclear force takes over. It pulls them toward the neutrons like they're all part of the same team. Inside the star, things get stranger the deeper you go. Near the surface, neutrons clump into blobs, kind of like a neutron gnocchi. A bit further down, these blobs link together into long chains, forming what scientists call the spaghetti layer. I'm getting hungry. At even greater pressures, the spaghetti chains fuse side by side, creating flat sheets. Think neutron lasagna. Keep going any deeper, and the lasagna eventually breaks down into a uniform mass. But even then, the structure isn't smooth. There are gaps, long tube-shaped voids that look a lot like penny pasta. So inside a neutron star, you've got layers of gnocchi, spaghetti, lasagna, and penny pasta. And each of them represents the mind-bending results of physics under insane pressure. Okay, I'm definitely having Italian for lunch today. Now, the recently discovered neutron star is part of a binary system located in a dense star cluster. This cluster is situated near the center of the Milky Way galaxy, approximately 26,000 light-years from Earth, in the direction of the Sagittarius constellation. The record-breaking spin of the star is extraordinary. If we take a period of not a second, but a minute, it'll be over 42,000 revolutions per minute. At the same time, the newbie ties with another neutron star, which spins at the exact same speed. Such extreme rotation rates are rare and make these stars cosmic outliers in terms of behavior and properties. Oh wait, we can't but mention our neutron star's binary partner. It's a white dwarf, a dense remnant of a star similar in size to our Sun. This white dwarf is pretty fast too. It orbits the neutron star once every 11 minutes. This makes the couple a binary system, with the shortest orbital period ever observed. Imagine a stellar object zipping around its partner faster than the time it takes to prepare a cup of coffee. Yep, that's the kind of speed we're talking about here. This tight, rapid orbit shows how powerful gravitational forces are inside the system. So, you might be wondering what makes neutron stars spin so rapidly. It's something called the conservation of angular momentum. Let me explain. When a massive star collapses into a neutron star, it shrinks dramatically. Such a rapid compression gives an instant boost to its spin. It's like an ice skater spinning faster when they pull their arms inward. And the smaller the star gets, the faster it spins, which results in extreme rotation rates. In binary systems like this one, neutron stars can achieve even faster spin rates. Their trick is to steal matter from their companion stars. This process is called theft. No, accretion. The stolen matter carries that very angular momentum, which adds to the neutron star's rotation speed. The accreted material can also build up on the neutron star's surface, eventually. It triggers powerful thermonuclear explosions. They release immense amounts of energy, temporarily making the neutron star shine up to 100,000 times brighter than our Sun. It allows astronomers to study the intricate details of these extreme environments. NASA's X-ray instrument on board the International Space Station, officially called the Neutron Star Interior Composition Explorer and thankfully nicknamed NICER, observed 15 thermonuclear explosions on the surface of our neutron star between 2017 and 2021. One of those bursts displayed a unique pattern called thermonuclear burst oscillations. Those are highly asymmetric patches of brightness on the burning surface layers of accreting neutron stars. This pattern matched the spin rate of the neutron star and thus confirmed its extreme rotational speed. But wait, the best part is coming. While neutron stars are already extreme, there's another class of them that takes things to a whole new level – magnetars. Now, magnetars are neutron stars with unimaginably strong magnetic fields, up to 1,000 trillion times stronger than Earth's magnetic field. These fields set them apart from other neutron stars. They can distort atoms in nearby objects, making life impossible anywhere near them. As for the energy density of a magnetar's magnetic field, it's so high that it's 10,000 times greater than the mass density of lead. Magnetars also produce bursts of X-rays and gamma rays that are so powerful they can temporarily outshine entire galaxies. These bursts are often triggered by star quakes, violent shifts in the magnetar's crust caused by their own magnetic fields. For example, a gamma-ray burst from a magnetar in 2004 was so strong that it disrupted Earth's ionosphere. It hit Earth, and it was so intense that several satellites picked it up. The SWIFT satellite, built specifically to detect gamma-ray bursts from across the universe, didn't just detect the blast, it got hit with so much energy that its sensors got completely overloaded. And SWIFT wasn't even facing the burst. The energy was so strong it passed through the spacecraft and still overwhelmed its cameras. If a magnetar was located as close to Earth as the Moon, its magnetic field would erase all credit card data on the planet by wiping the magnetic stripes clean. Whoa, that's the level of power we're dealing with here. Magnetars are extremely active, but for a relatively short time. Their intense magnetic fields decay after about 10,000 years. After that, they stop emitting strong X-rays and gamma rays. Astronomers think that there are at least 30 million inactive magnetars in the Milky Way galaxy alone. These silent cosmic relics are scattered all over the galaxy. Neutron stars and magnetars serve as laboratories for extreme physics. They allow astronomers to have insights into the behavior of certain matter under conditions you can never replicate on Earth. The incredible density of these objects helps scientists figure out what happens when protons and electrons get compressed together to form neutrons. This creates states of matter that don't exist anywhere else in the universe. These violent explosions on neutron stars and magnetars also play a critical role in the formation of heavy elements like gold and platinum. These elements get scattered all over the universe during these energetic events, eventually becoming parts of planets and stars and you and me. Oh, by the way, NASA's NICER instrument has played the key role in uncovering the mysteries of neutron stars. Its ability to detect X-rays with high precision allowed astronomers to study the rapid spin of the neutron star we've been talking about and the thermonuclear bursts that occur on its surface. So, what could be nicer than that? Hey, look at this blazing monster. It's a white dwarf. These stars are known for gobbling up passing objects, and one day, these objects might be the planets of our own solar system. According to a new study, parts of the solar system will be pulled into a white dwarf star, crushed up, and eventually ground into a fine dust like coffee beans in a blade grinder. Hey, you like that analogy? Now, white dwarfs are a final stage of a star's life. It's a small but very dense star that's typically the size of a planet, the result of a low-mass star exhausting all the nuclear fuel in its center and losing its outer layers as a planetary nebula. When our sun turns into a white dwarf, and it is bound to happen sometime, it'll destroy the asteroids and moons around Mars and Jupiter. They will be pulverized by its gravity. Earth, though, will be swallowed up even before the sun turns into a white dwarf. But it won't happen for another 6 billion years. Researchers working on this topic have come to such conclusions by observing what happened to space bodies, asteroids, moons, and planets that were passing close to 3 white dwarfs. For 17 years, they observed and analyzed transits. That's when the brightness of a white dwarf dips because of an object in a stable orbit passing in front of it. In the case of white dwarfs, we can predict such transits and use them to study the stars themselves and celestial objects passing by them. So, when something gets too close to a white dwarf star, the star's immense gravity rips it into smaller and smaller pieces of debris. The team also found out that transits of such debris are chaotic. Plus, this debris is oddly shaped, which means that it is being devoured further. The first white dwarf used for studying the transit process, this here guy, seems steady and well-behaved over the last few years. Well, until scientists found some evidence of a massive catastrophic event that occurred in 2010 or so. The next star dims irregularly every couple of months before brightening again. And the third dwarf star used to behave close to theoretical predictions. It had transits that varied in number, shapes, and depths. But the latest study has shown that the transits are now completely gone. And this indicates the unpredicted nature of transits. One minute you see them, the next, poof. The reason might be the chaotic environment they have to exist in. As for our own solar system and our planet in general, its fate looks pretty sad. Earth will be swallowed by the expanding sun even before our star turns into a white dwarf. As for the rest of the solar system, located further from the sun, some of the asteroids between Mars and Jupiter, as well as some of Jupiter's moons, will be destroyed later. Oh well, they're likely to get dislodged and travel too close to the white dwarf. Now, at the same time, astronomers aren't 100% sure that it's exactly what will happen with our solar system. So I guess we'll just have to wait and see, for like 6 billion years. Speaking of white dwarfs, scientists have recently found one that has a bizarre metallic scar on its surface. This blemish could have formed after the star ripped up and ate a tiny planet orbiting it. White dwarfs with traces of metal in their atmospheres aren't rare. These traces are left by planets falling into stars, affected by their gravity. Experts have long thought that such metal should be distributed evenly across the surface of such polluted white dwarfs. But a new study has discovered a white dwarf with a weird concentrated patch of metal. This star was monitored over a period of 2 months with the help of the Very Large Telescope in Chile. The researchers found an opaque patch of metal. It was located over one of the star's magnetic poles and blocked some of the star's light as it rotated. Based on this position, astronomers concluded that the material could have been funneled into the star by its powerful magnetic field. This process is similar to one causing auroras on Earth, where charged particles follow the magnetic field to the surface. Now, the planet destroyed by the white dwarf was most likely very small, around the same size as asteroid Vesta in our solar system, which is a mere 326 miles across. Its debris is now prominently displayed on the host star's surface. It makes it easier for researchers to examine what the planet's geochemistry was before it was devoured. Such a study might even turn out to be one of the best ways to observe small worlds beyond the solar system, even if such a world has already met its demise. There might be many more scarred stars like this one. The one in question was the first, but probably not the last. Even better, astronomers have already discovered 2 white dwarfs that seem to have similar scars. Making repeat observations of such stars might help us unearth, pardon the pun, no, I meant to do that, unearth even more secrets and make more discoveries. Another bizarre white dwarf discovered not long ago seems to have stopped cooling due to the formation of internal crystals. It challenges existing theories on star aging and also questions the method of stellar age estimation. But scientists might have understood why it may be happening. White dwarfs are believed to be dead stars. They keep cooling down over time, and normally this process can't be reversed or paused. But in 2019, the European Space Agency's Gaia satellite discovered a number of white dwarf stars that had stopped cooling for more than 8 billion years. It might mean that some white dwarfs can generate a lot of extra energy, which is at odds with the classical dead star theory. At first, astronomers couldn't figure out how it might happen. But in the end, more than 97% of stars in the Milky Way galaxy turn into white dwarfs. Astronomers have long thought that such stars are at the end of their lives. After depleting their nuclear energy source, they stop producing heat and cool down. Eventually, the dense plasma in their insides freezes into a solid state and the star solidifies from inside out. The whole process can take billions of years. But the new research claims that in some white dwarfs, this dense plasma doesn't simply freeze. Instead, its solid crystals forming upon freezing become less dense than the liquid and start floating around. They displace the heavier liquid downward. The movement of heavier material toward the center of a white dwarf releases gravitational energy, and this energy is enough to interrupt the star's cooling process and halt it for billions of years. Now, this explanation actually matches all of the properties of the unusual white dwarf population. But this is the first time such a transport mechanism has been seen in any type of star. And that's incredibly exciting. A totally new astrophysical phenomenon. But why does it happen in some stars but not in others? It most likely depends on the composition of the star. You see, some white dwarf stars are formed by the merger of two different stars. When they collide and form a white dwarf, it changes the composition of the star, which allows the formation of floating crystals. So this discovery might mean that astronomers will have to review the ways they use to determine the age of stars. At the moment, white dwarfs are often used as age indicators. The cooler a white dwarf is, the older it's believed to be. But now, we already know about possible delays in the cooling process of some dwarfs. It makes the popular age determination method more unreliable. Some stars of a given temperature may be billions of years older than we previously thought. The recently uncovered transport mechanism within white dwarfs means that some of these stars can be shining as bright as normal for billions of years. This complicates age dating and the use of white dwarfs to reconstruct the formation of our galaxy. Hey, stay tuned.
Most of those twinkling dots scattered across the night sky seem unreachable. But one of them is Betelgeuse, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Betelgeuse. It's one of the brightest stars we can see from Earth, and it's just 640 light-years away. No big deal. Betelgeuse has a blue-white O-type star, which is one of the hottest types to exist. Betelgeuse was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star, and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Betelgeuse. It burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Betelgeuse replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Betelgeuse spinning way faster than it should for a star of its size. Huge stars like Betelgeuse are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Betelgeuse's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Betelgeuse shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Betelgeuse's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Betelgeuse isn't as smooth as our sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the sun, but Earth's entire orbit around the sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Betelgeuse could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Betelgeuse dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Betelgeuse clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Betelgeuse cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Betelgeuse's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Betelgeuse might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Betelgeuse run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Betelgeuse supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Betelgeuse will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Betelgeuse explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Betelgeuse might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Betelgeuse is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Betelgeuse might have less than 300 years of fuel left in its core. They say that Betelgeuse is known to expand and contract regularly, and its pulsation pattern hints that Betelgeuse is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VYCMA in our galaxy is thought to be closer to going supernova than Betelgeuse, and it's been dimming steadily over the past century, unlike the relatively stable Betelgeuse. If Betelgeuse was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Betelgeuse as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Betelgeuse won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm.